Okay, very well. So we can start with the second talk. We have Florian Zeiser from the Max-Planck-Institut for Mathematics in Bonn, and he will talk about Poisson linearization using Nash-Moser methods.
Thank you very much for the introduction, and thanks for the opportunity to speak here. And even more, thanks for organizing this workshop in quite challenging times, I can imagine. So I will talk about the Poisson linearization question and well, the use of Nash-Moser method. And this is part of the project of my PhD thesis, which I did join with my supervisor, Johan Makut, who is also here. And I actually just realized that I think about 50% in the audience have seen parts of this talk, at least in some shape or form. So I hope also for those, maybe you can improve your knowledge a bit, or well, maybe use your advanced knowledge to ask advanced questions at the end. So we'll see. Yeah, I want to start. I need help. No. I think
did you switch it on?
Oh no, it does something. Oh, awesome. Okay, I want to start with a very basic definition of a Poisson bivector. So that is just a bivector field on a manifold. So for me, a manifold is always a smooth manifold, finite dimensional. And the Poisson condition is phrased in terms of the Scout-9 bracket of the bivector with itself is 0. And the question I want to tackle is that of the question of a local normal form of the bivector. Okay.
Let's do this. Oh, please go.
Okay. And well, the first step in that direction was done by Alan Weinstein in his paper 1983 about with the. Ooh. Yeah, okay, that's the problem. Okay, so the first step into the direction of a local normal. So first, what is a local normal form? Well, it's an expression which is, let's say, a standard expression such that one can always find a chart to map our actual structure into that standard structure. For example, for complex structures, one has this, that one can always map the multiplication by the complex structure to some Cn. And for Poisson geometry, the first result in this direction was by Weinstein, who proved the splitting theorem, which basically states that one can locally split the Poisson bivector into a symplectic part and to a transverse part, which vanishes. So more concretely, we take a point on our manifold and we look at the rank of the corresponding matrix of the coefficient, which gives the rank and the corank R. And then we can find coordinates P, Q, and X, such that the P and Q's form the local coordinates of the symplectic leaf, so that gives rise to a, let's see, to a symplectic, to a non-degenerate bivector, so Poisson vector structure which comes locally from a symplectic form, and then to a Poisson bivector on the transverse part, which vanishes at the origin. So in order to obtain a local normal form, one can focus on Poisson structures which vanish at the point. And that leads us naturally to the question of linearization. And for that, we look into linear Poisson structures, and linear Poisson structures are associated in one-to-one correspondence with Lie algebra structures. So in a vector space, one has a Lie algebra structure, and then there's a one-to-one correspondence to a linear Poisson structure on the dual vector space. And the term linear comes from the fact that if one takes the Poisson bracket maybe of two linear functions, then the result is also a linear function. So that's where the term comes from. And the correspondence is given by this simple formula. So given an element in the dual of our Lie algebra xi and two elements x and y on our Lie algebra. So here we identify the dual of the dual. So the cotangent space at the point psi with the Lie algebra, and we evaluate our Poisson structure at two elements x and y, and then this is just given by evaluating of the bracket of x and y at xi. And this gives this one-to-one correspondence between linear Poisson structures and Lie algebra structures. So now, how does this come into play for Poisson structures which vanish at the point. So for this, we take a manifold and a Poisson structure which vanishes at the point. And then what one obtains is a Lie algebra structure at the cotangent space of this point, which is given by this formula. So for two functions f and g, we can form any cotangent vector by taking the differential of arbitrary functions, and then the Lie bracket is given by this formula, and that's, if you want to think of it in terms of Lie algebroids, maybe it's just the anchor map of the isotropy Lie algebra of the corresponding Lie algebroid associated to the Poisson structure. And well, this Lie algebra structure is called the isotropy Lie algebra, correspondingly of the Poisson structure at this point. And well, as we just have seen above, every Lie algebra corresponds to a linear Poisson structure on the dual. So what we get is, a linear Poisson structure on the tangent space of the point, which we call the linear approximation. And now the natural question is, given a linear approximation, can we find a local diffeomorphism mapping our actual Poisson structure to our linear approximation? So that is exactly the question of linearization. And the answer might depend on the Lie algebra. So we call a Lie algebra Poisson non-degenerate if for every such ripple of a manifold, a Poisson structure, and the point x where the Poisson structure vanishes, and if the corresponding isotropy Lie algebra is isomorphic to our Lie algebra, then we always can find such a diffeomorphism. And if that's not the case, we call the Lie algebra Poisson degenerate. And this linearization question is really, because it's really a local question, right? One can phrase this simply in terms of Poisson structures on some Rn, which vanish at the origin. And then the question is, can one map it to the corresponding linear? Can one find the diffeomorphism of the corresponding linear Poisson structure associated to the isotropy Lie algebra? And one can ask the question not only in the smooth category, but also in terms of power series. And the first result in that direction was in terms of power series. In the same paper, Ellen Weinstein proved the splitting theorem. He showed that for any semi-simple Lie algebra, or any semi-simple Lie algebra is formally Poisson non-degenerate, meaning that one can always find a local a power series which is invertible, mapping well, the corresponding power series of the Poisson structure to the linear one. And well, we are more interested in the smooth case. So let me maybe briefly recall how the situation looks for semi-simple Lie algebras in smooth case, and for that we need the Iwasawa cube composition. So maybe a brief reminder that is obtained by taking a Cartan involution, which one always has, so a Lie algebra automorphism, which squares to 1, and one has the +1 and the -1 eigenspace, and the 1 eigenspace gives rise to the k. So that's the k part, and then from the -1 eigenspace, one takes the maximal abelian subalgebra, and that's the a part. And then to obtain a vector space decomposition, one can add an abelian, an nilpotent subalgebra, but I don't want to go into this because it's so important for what comes next. And then what we know for semi-simple Lie algebras for this linearization result is the following. So already, again, Weinstein in the same paper showed that in the smooth case, it's quite different, because for the Lie algebra SL2R, he showed that that one is Poisson degenerate. So one cannot always find such a diffeomorphism. And just 2 years later, Kohn proved that if the semi-simple Lie algebra is in fact compact, then one can find a diffeomorphism. And he did this using the Nash-Moser method, which I will come to, well, in a minute. And then later, Kleinig and Fernandez proved the same result, but using really geometric methods, or not the Nash-Moser method. And then the next result were, again, negative results by Weinstein and Monnier and Song. So they showed that if the dimension of A is at least 2, or if the dimension of A is 1 and K is not semi-simple, the compact part non-simple, then one cannot always find such a diffeomorphism, which leaves us with the case where the dimension of A is 1 and the K part is semi-simple. And the lowest dimensional example of such a Lie algebra is that of SO3-1. And as part of my PhD thesis, we showed that in this case, one can find such a diffeomorphism. And well, the other cases remain still open. But the conjecture is that they are also Poisson non-degenerate. And the way we prove this is similar to Con using a Nash-Moser method, which I want to come to next. Okay, so that's the part about the linearization question. And now I want to turn to the part of this proof and also the part of Con's proof, which uses the Nash-Moser method to obtain this diffeomorphism. And well, one important ingredient is that of Poisson cohomology. So that's a cohomology which is naturally associated to any Poisson structure. It's formulated on the space of multi-vector fields on the smooth manifold, and the differential is just given by taking this Cartan 9-Haus bracket and plugging the Poisson structure into the first slot, and that operator increases the degree by 1, and one can show that it indeed squares to 0 using the condition that phi is a Poisson structure, so that this Cartan 9-Haus bracket of phi with itself is 0. And then the corresponding cohomology is what's called Poisson cohomology. And of special interest to us is the second cohomology group, because the second cohomology group controls the deformation. So that is heuristically has the interpretation of giving the infinitesimal deformations of the Poisson structure modulo deformations which come from diffeomorphisms. So in order to find such a diffeomorphism, what we would like to have is a vanishing of the second Poisson cohomology group. And that's indeed what we will need. Okay, now in our case, we want to show the linearization result. So of particular importance is the Poisson cohomology of linear Poisson structures. So for this, we look at the Lie algebra with a linear Poisson structure. And their Poisson cohomology really has a different interpretation in terms of Lie algebra cohomology with coefficients on the smooth functions of the dual. And then, so here the smooth vector fields are simply isomorphic to the exterior algebra tensor, the smooth functions. And then the differential just becomes the Eilenberg-Chevalier differential, where the representation on the space of smooth functions is induced by the Poisson bracket or by the coadjoint action. Okay, and what will be important for us is the following short exact sequence. So here in the middle, we have the smooth functions on the dual of the Lie algebra. And here we map with the infinite jet map at 0 to the formal power series. So this is just taking the Taylor series of a function at the point. And then on the other side, it's just the kernel, what we call flat functions. So functions which are 0 and whose Taylor series at 0 is 0. And what we do is we, of special importance, are multi-vector fields which are flat. So that are just multi-vector fields where we exchange the smooth functions here simply by the flat functions. And we denote them with an index 0 here. So that comes next. And then one of the two main ingredients to prove the linearization result is the following theorem. So given a Lie algebra, which should satisfy two conditions. So first, it should be formally Poisson non-degenerate, meaning one can always find the formal power series such that we can linearize, and which should admit homotopy operators. And with the word homotopy operators, I mean a map H1 from flat bivector fields to flat vector fields, and H2 from flat 3 vector fields to flat 2 vector fields, which are cochain maps between 0 and their identity on the flat bivector fields. So in terms of formula, that's exactly the condition we want to satisfy them. And they should satisfy good estimates. And I will specify the good estimates in a second. So these are the two ingredients we need on the Lie algebra. And basically the statement is, in such a case, we can find such a diffeomorphism. And well, maybe that's the point where I want to say what I mean by good estimate. So let me see how I do this in the best way possible. If I write here, can people online see me?
Now they can better. I think if you write on that side there.
On which side?
Well, I mean, not where there is the,
Okay,
like
so
there.
here.
Oh, okay.
You can mute it.
Okay.
It's easier solution.
Let's see.
But then I don't need some light. We don't like the light.
Okay. Yeah, so in order to say what good estimates are, I want to define some semi-norms which are very special for the class of flat functions. And for this, well, we take a multi-vector field W, a flat one, or any, really. And then we define the norm n comma k. So here n and k are just natural numbers of W to be.
Is it possible to write a little bit bigger, because online it's quite hard to see?
Of course. Okay, then maybe I need more space. Is that readable?
To me, honestly, not that much. I don't know how others feel about this. Just the quality of the camera isn't that good, unfortunately.
Oh.
I'm not sure how to sort this out.
Well, maybe I can put my slides online afterwards and put it in the slides. So I don't have a better solution.
Yeah, perhaps that's the better solution, the best solution. But yeah, maybe just say out loud what you're writing, okay. So then we can sort of follow.
Yeah. Okay. I'll try to do that. Okay, so we have a flat multi-vector field and two natural numbers, and then we define the norm of, or semi-norm of W with two indices n comma k. So let's say we are some 4. That is just defined to be the standard nth norm of Wx, but then with the weight x to the minus k. Yeah, and that is really a semi-norm which one can only use for flat functions, because otherwise it would not be well defined. So it's very specific for them. And then what good estimates?
What is this norm n again? Sorry.
N is the standard Cn norm. So one takes, well, the supremum over all derivatives up to n.
Okay.
And the supremum over all points in that one. Good estimate. We require our homotopy operators hi of W. So the n-case norm of hi of W should be bounded by some constant times n plus e in the first index, and then k plus e times n plus 1 in the second. Yeah, so that estimate does not look very nice. So, but that's somehow what we get from our. So maybe I should go to right. So d is again some natural number. Yeah, so that's basically that is not an estimate which we thought about. So that's nice, but that's basically what we get from the. Yes.
So the one.
Oh yeah, no, the D should be universal. Yeah, yeah, that is actually quite important. Very good.
So there exists a D such that for all n and k this is true.
Indeed.
And the C is also like constant for each, like the same constant C.
The C is the same constant. Or no, the C might depend on n. The C might depend on you, but the D is independent. That's important part. Yeah. So maybe a comment to what Con did in the compact semi-simple case. So in the compact semi-simple case, well, first of all, his operators were really defined on all the vector fields, and the estimates he had there were basically the estimates which you have when you do not have the indices. Yeah, and maybe another remark is if you just would use also the standard CN norms, the natural way to estimate this here would be just to use the formula for the Taylor expansion with integral remainder. Then we would get an estimate which, well, okay, not to be completely precise, but what one would get here is something of the form maybe D1 times N plus D2, where D1 depends on T and the D2 depends on also the keys. But the problem with this estimate is it's for the D1 bigger or at least 2, the estimate is too bad to apply the Nash-Moser technique. So that's why we really need this changed semi-norms in order to do the Nash-Moser estimate in our case. Okay, so that explains it. Okay. And then I want to say a couple of words about the proof. So the basic idea is, well, the conditions for the condition for the theorem already might indicate is that we divide our problem into what we call a formal part, so a part which is taken care of by power series considerations, and one part which is taken care of by using this flat functions and multi-vector fields. And for the formal part, well, one already knows that one can, by assumption, that one can formally linearize the Poisson structure, and then one uses Borel's lemma to extend this power series to an actual local diffeomorphism. So Borel's lemma just says that every power series can be extended to a function whose Taylor series at that point is that power series. So what we may assume is that the difference, so the infinite jet at 0 is 0. So in other words, the difference between our Poisson structure pi and the linear one is just a flat bivector field. And then for the flat part, we adapt basically Con's iteration just to the purely flat setting and use the Nash-Moser. And that's also, well, I'm very curious actually if that is something, well, which is only helpful in the Poisson case, or maybe for foliations to divide this problem, or if there might be also other geometric problems where this might be of use, or maybe it's also just because we weren't able to find better homotopy operators that this is helpful in our case. But that is really something which would be quite interesting to understand. Now to the actual Nash-Moser iteration, I have the last slide, which should give the idea of the iteration. And for this, we look at the following map. So we have our Poisson structure, which is the linear one plus something flat. And then we look at this map. So here, phi of x should denote the time one flow with respect to the vector field, which is given by h1 applied to z. And then we take the difference of the pullback of this time one flow of pi minus phi g. So here I just want to give an idea. So one, of course, has to take care of the fact that, well, that one has different domains and such, but that I want to ignore for a fact. So let's assume maybe that is a diffeomorphism, and that's what we have. And I also want to assume that we actually are working with Banach spaces. So we only have one norm, which defines the whole topology, and that we have this simplified set of estimates, so that the homotopy operators of Z, the norm of them can just be estimated by the norm of Z, and we assume them to be smaller than epsilon, some small parameter. And basically what we want to show is
Because we can't see the application if I read correctly, but I also was wondering what it meant. Lucas, is it everything right?
I'm sorry?
Did some message appear to you or everything?
I didn't see anything out of the ordinary.
Okay, then it seems that you can. There was a Zoom that gave some message. It was not clear to us, but it's fine.
Oh, no, everything looks okay here.
Okay, basically what one can show is in a more, oh yeah. What one roughly obtains under this assumption is that the map one has is actually a contraction. So that the norm of the image can be bounded by epsilon squared. Yeah, and that way what we do is we just iterate this process, and then what we want to get is that first of all, that the limit of this iteration gives us our linear Poisson structure, and that the concatenation of all these timed one flows gives us actually this diffeomorphism. And one can make this precise and show that it works also in our setting, which is actually that of a Fréchet space. So we have not just the one norm in which one has a Banach space, so actually a family of semi-norms. And to do this, what one in particular needs, because one has this increase, let's say, in the derivatives here, d, what one needs is one needs to plug in here what is called a smoothing operator. So that somehow takes care of getting back. So first we increase the derivative somehow by this homotopy operators and the smoothing operator to allows us to get back to our original n in order for the algorithm to work. Because otherwise, like with every step, we would take higher and higher derivatives, which would not work. Okay, and I think I would leave it at that, and I would like to thank you for your attention. I'm sorry for the technical.
So thanks again for the talk. We are sorry for the technical problem on our side. Are there questions? Anything online?
So perhaps I have a question. So you said it was very important to have the G universal. So now that you sketched the proof, can you say more where it's happening? It's appearing to have this G universal.
Well, basically, what one oh yeah, the question is okay. So
you can also do. You don't have to, but
so basically, the problem is one needs this convergence for all the NK norms, because one needs conversions in the Fréchet space, and for this, yeah, you cannot have some T's which somehow increase to infinity or so with increasing NK, because otherwise we do not have control over this conversion. So that's why one needs some university.
Further questions? Also online, there is anything else? Lucas?
No, so far everything's totally clear apparently.
Okay, then we can thank Florian again for his message.